All right, so when exploring a data set for the first time, it is important to understand the data and the process behind it. So we want to look at summary statistics of the data and attach the results to the report. Let's do df.describe, and this is going to show us the summary statistics for all quantitative variables in the data set. And for this, we're calling this exploratory data analysis. If we look this up, exploratory data analysis. I spelled the word wrong, but that's fine. So EDA in statistics, exploratory data analysis is an approach to analyze data sets, summarize their main characteristics. So that's what we're doing in the first portion of this project. We're just kind of looking at what the data looks like. So here are the summary statistics. We have the quartiles. We have some of the at the first moment, which is the mean. We have the standard deviation, the count, and so on. So we have 4,860 points of data. And we can use Seaborn. So let's import matplotlib and Seaborn. Let's say let's import matplotlib pyplot. So matplotlib.pyplot is PLT. Let's import Seaborn as SNS, and let's do the magic command so that the matplotlib matplotlib inline, so that the matplotlib plots can show up in the in our notebook file. I'm going to use dark grid for the style. You can use any style you want for the project. Preferably, it will not be default, but you can use dark grid, white grid. You can use a 538 or any of the other options from pyplot or Seaborn. So let's start with looking at a pair plot. So again, this is only going to be the quantitative variables. And it's going to take a few seconds to run, just because there's so many. There's so much in this file, in this data frame. But we're going to try to look for linear relationships among the variables. So we're trying to look for linear relationships so that we can measure it with a regression. Outputting a plot always takes more time for the computer than just outputting a just a number or a data frame. But every time it outputs something, that's or prints, it takes time to do. So here we go. Along the diagonal, we have our histograms. We're trying to measure. We're trying to estimate or predict closing price. So here it is. Right here, so closing price and current price seems like it's a perfect function of one another. So we, of course, couldn't do much with that. MOS is just descriptive. That means nothing for us. And here we have a square foot. So we have this total square foot. That seems like it could be promising. That seems reasonable. Then we'll continue. So then from this, let's now create a heat map. So we use sns.heatmap. We're going to create a correlation matrix. So remember df.corr. This gives us a correlation matrix. So along that diagonal, you have the correlation of something with respect to itself. So current price correlated with current price is going to be 1. And then everything else you have, so here, right here would be the correlation between close month and current price and so on. So we're going to put this in a heat map. Let's do heat map. Let's turn on annotation, and let's set the CMAP to be blues. And we can't forget our parentheses here. And here's our heat map, so you can see all the ones that's colored accordingly. So if we're trying to find which variables may have the strongest linear relationship with closing price, current price, of course, but that wouldn't be a good one to have. Square foot total seems promising. The year built seems promising. The number of beds seem promising. The number of baths seem promising. Baths full, baths half. All of these seem promising, except those dealing with time. Let's do this again. This time, let's look at a current price. Let's look at a square foot total. Let's look at the year built. Let's look at beds total. Let's look at baths total. Let's just focus on this. So let's create a heat map of all of this. So I'm going to do another correlation heat map. I'm going to turn on annotation, annote equal true. I'm going to do the CMap equal blues. I'm going to close it. Now we get another correlation matrix. So now we can see a little bit clearer that all of these have a reasonable linear relationship. And it's not the fact that they're positive. They could be negative. It's the absolute value. The closer the absolute value of correlation is to 1, the stronger that linear relationship. And that's all correlation can measure is a linear. So if it went like a sine or like a polynomial or a curve or an S shape, then the correlation may not be a good measure because it wouldn't be linear, even though there is a relationship. So now we're so this is this seems good for now. But something else to keep in mind is collinearity. So we have we don't want variables to be functions of other variables. Notice that I took out baths full or baths half. Those, if I include those, then you'll really see it. So I'm gonna do baths full. I'm gonna do baths half. I'm going to include those. You see that these are a perfect relationship with one another. The number of total baths and full baths, it's a perfect one-to-one relationship. That would be bad. You couldn't include both. Maybe you could include the number of total bathrooms, but you can't include the number of total and the number of full baths. That would be, they're collinear with one another. You also have bedrooms and bathrooms. They are also reasonably collinear with one another. 0.64 correlation. So that could also be a potential problem. We'll get a little bit more detail into that later on. So that's it for this video. Next one, we'll continue with our exploratory data analysis.